The last topic we have to learn about is rates of reaction. So, in order to talk about rates of reaction, first we need to talk about collision theory. So, the idea of collision theory is that in order to react, particles have to collide, but not every single collision results in a successful reaction. So, in order to actually have a successful reaction, there are a few things that must be true. The particles have to react with sufficient energy. So, just like a gentle collision won't help the particles react, they need to collide with enough energy. Also, particles need to have the correct orientation. So, if particles kind of bump in a way that isn't aligned with each other, that will not result in a successful collision. They need to be aligned in the right way. So, there are a couple strategies to increase the rate of reaction. Each strategy addresses one of those factors that we just talked about. So, if you need to have successful collisions, then just increase the collisions in general. The more collisions you have, then hopefully one of them will be successful. The way you can increase those collisions is depends on whether you're dealing with solids or gases um, or liquids. So with gases, you can increase the pressure. If you've got an increased pressure, you have more particles in 1 liter of volume. If you have a solution, then you can increase the concentration of the solution because again, you've got more concentration. You've got more particles in 1 liter of solution. If you are dealing with solids, you can increase the surface area. You can have more exposed particles. And this diagram over here shows the idea of surface area. Here, there's only like 1, 2, 3, 4, 5, 6, not this one, 7 particles exposed. But if we crush that solid into separate particles, then all 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 particles are exposed. And so by increasing the surface area, you're exposing more particles so that they're available for collisions. For any reactant, whether it's solid or gas or in solution, increasing the temperature causes the particles to move faster, which means you're going to have more frequent collisions. Not only are you going to have more frequent collisions, those collisions are going to be more powerful. And so that brings us to our second point. If you increase the energy of the collisions by increasing the temperature, then the particles are going to move faster, causing those more forceful collisions. Therefore, that minimum energy needed to get the reaction started is more likely to be met. So we kind of achieve that minimum activation energy needed to start the chemical reaction. And if you think about this, even like if you have a Bunsen burner and all it takes is a spark to get it going. Once you have that activation energy, that spark to get the Bunsen burner lit, it continues to burn on its own because it creates enough. It's an exothermic reaction. It creates enough energy to sustain that flame. This activation energy explains that hill on those reaction pathway diagrams that we reviewed when we were learning about combustion reactions and bond energy calculations, but also learned about in chapter 1. And so at high temperatures, particles are going to have more energy and therefore less hill left to climb in order to achieve that activation energy. So let me show you that reaction pathway diagram like this. So here, if my reactants start with this much energy, I have to climb this big hill to actually start making product. But when I heat up my reaction mixture, I'm starting more like here. So I don't have so far to go to actually make my chemical reaction happen. Another way to look at how the increasing the temperature increases the rate of reaction is by looking at a Maxwell-Boltzmann distribution. And we've looked at these before. Remember, these show the number of particles moving at different speeds at one particular temperature. So at one temperature, kind of my average kinetic energy might be sitting at about here. And so that would indicate kind of the temperature at which my particles are moving. Keeping in mind what this is showing us is that at any given temperature, particles move at a variety of speeds. It's not like if you've got one temperature, all those particles are moving at a speed, and then at a higher temperature, every single particle is moving faster. That is not true. There are always some slow particles, some fast particles. It's the average that gives that is an indication of the temperature. So particles with enough energy to react that have achieved that activation energy are shaded in here on the graph. So if I increase the temperature, where the average temperature isn't like here anymore, it's now here, you can see that with that increase in temperature, now my activation energy here, I now have a larger region shaded in gray. So at temperature 2, particles move faster on average, and therefore I have more particles moving with enough energy to react in that orange and gray shaded regions to the right. So at high temperatures, more particles have the activation energy needed in order to react. Another way to cause a reaction to happen faster is to force the correct orientation of the particles so that you're more likely to have a successful collision. When you do that, you decrease the activation energy. So anything that kind of decreases the activation energy will increase the rate of reaction. And the most common mechanism for doing this are catalysts and enzymes. These are chemicals that reduce activation energy. That's kind of their definition. They reduce activation energy needed for a reaction to happen. Some of these chemicals work by holding molecules in a correct orientation so that less energy is needed for a successful collision. And so we'll look at reaction pathway diagrams to show and a Maxwell-Boltzmann distribution to show how catalysts and enzymes work to make the reaction happen faster. So in a reaction pathway diagram, what an enzyme or what a catalyst does is they make the hill smaller. Instead of having to put in all this energy to make the chemical reaction happen, we hold the molecules in the correct orientation or some other mechanism to reduce the activation energy. So my hill is very small now, and more particles have that smaller amount of energy, and therefore more particles are able to react. Looking at a Maxwell-Boltzmann distribution, we aren't changing the temperature of our reaction mixture. But when you reduce the activation energy, instead of just looking at this area under the curve, those limited number of molecules that have sufficient energy, we have a larger area of particles that have sufficient energy to achieve a successful reaction just because we lowered that activation energy. We've lowered the threshold, we've lowered the bar. Therefore, more particles have the energy needed to react. I hope this helped.